Today we're going to look at the behavior of waves. Now I know for a lot of these things it will be helpful to see them in person, so we are going to do demonstrations in class. So for this lesson I just want you to concentrate on getting the vocabulary terms and their definitions. So let's get started. The first thing that waves can do is called reflection. This is the turning back of waves due to an abrupt change in the medium. You basically want to think about a wave coming in, hitting a hard surface, and then it's going to bounce back. Now you might see this dotted line right here. This is called a normal line. It's an imaginary line perpendicular to the surface, and we use that for the law of reflection, which states that the angle of incidence equals the angle of reflection. So if you can imagine a wave coming in, we would measure the angle of incidence from this imaginary normal line, so it's going to be measured outward. And then once the wave reflects, it will reflect at an angle that's equal to the same angle that it was incident. Now we use an imaginary perpendicular line or normal because our surface might not always be straight. It could be a jagged edge or a curved surface. But if we measure from this normal line, it's going to be uniform all the time. This slide just shows you some different pictures. So if we imagine some water waves and they're headed towards a barrier, if we imagine the normal or imaginary perpendicular line, we could see the angle of reflection and the angle of incidence are going to be equal to each other, and it shows us the way that the waves would get reflected. The next term is refraction, and this is the bending of waves as they pass from one medium to another. Remember that the word medium just simply means a material. So instead of a hard surface for the wave to bounce back upon, the wave can keep going, but it's going to change its direction slightly. So sometimes it might bend outward away from the normal, and sometimes our waves might bend inward toward the normal. It depends on the density of the two media, and this is something we'll discuss in a later chapter. Refraction sometimes is referred to as the bent stick phenomenon. I don't know if you've ever looked at something where part of it's sticking out of water and part of it's underneath water, but it kind of appears to bend a little bit. This would be an example of refraction. You see that distortion. This is just a fun picture for you with an example of refraction. And this slide just presents some different pictures and ways of looking at refraction. Feel free to pause the video and write down any extra information that you feel is necessary. Next, we have diffraction, and notice that these words are going to be really similar to each other, so it's going to be important that you pay attention to detail. We have reflection, refraction, and now diffraction. Diffraction is the bending of waves around and behind the edge of a barrier. So you want to think about a solid object that's actually in the way of our waves, and those waves have to bend around and behind that object. Our next behavior of waves is something called interference, and this is the effect of two or more waves traveling through a medium or a material. When these two or more waves meet, we're going to add their displacements or their amplitudes. There are actually two types of interference. Our first one is called constructive interference. This would be when the wave displacements or amplitudes are in the same direction. So as you can see, we would have two waves where the part of the wave is below the equilibrium, and then at the same time, both waves have a part of their wave above the equilibrium line. We call this in phase with each other. Notice that when we add the two amplitudes together, we get a larger amplitude resulting in one combined wave. You could also overlap the two waves, so I did the same thing where each of them have their amplitudes either both positive or both negative, but in this case they're different. So if I were to combine these two, I would take the amplitude of this one and add the amplitude of the second one and come up with a wave that's much taller that combines those two amplitudes together. And then I could do the same thing for the negative part of those amplitudes or displacements. As long as the amplitudes or displacements are either both positive or both negative, that would be constructive interference. Next, we have destructive interference, and as you can imagine, that's when the wave displacements or amplitudes are going to be in opposite directions. So we would have something that looks like this, where we've got one wave with a negative amplitude and the other one has a positive amplitude. These are said to be 180 degrees out of phase, or they're also a half of a wavelength out of phase. When we add the two waves together, destructive interference results in those waves canceling each other out. Again, we could either look at the two waves separately and add them together, or you can overlap them, but the result is going to be the same. When you add them together, those waves are going to cancel each other out for destructive interference. So here's another slide to present constructive and destructive interference for you. Feel free to add to your notes if you see fit. Next, we're going to discuss superposition. I have the definition already filled in for you. I know that sounds like a lot of complicated vocabulary words, but basically it means add the amplitudes of your waves. Now for our example, I chose what are called square waves because they're a little bit easier to add, so you should have this picture already in your notes. And then what I've done is drawn a line each time either of our two waves changes its direction. So what we're going to do is break this into sections and add them individually. So I've got an equilibrium position for wave number 1 and an equilibrium position for wave number 2. So what we're going to do is add the amplitudes of each of these two waves together and get our resulting wave once they are superimposed with each other. So we need to have a reference line. So I'm going to go ahead and make my equilibrium position right there. Now let's look at each section individually. For this first one, the amplitude is positive, and to keep things simple, I'm just going to say that it has an amplitude of +1. And then my second wave, notice that it doesn't go up at all. It stays on the equilibrium line. So it has an amplitude of 0. Now I'm just going to add +1 and 0 together, and this gives me a result of +1. So I'm going to draw my wave going up and having the amplitude of +1. Now let's do the next section. My second wave still had an amplitude of +1. Now my second wave also has an amplitude of +1. So when I add 1 and 1 together, my resulting wave should have an amplitude of +2. So I'm going to go ahead and draw that in. Notice that it's a total of +2, not 2 additional steps up. So everything's measured from that equilibrium line. So from 0, a total of +2 for the amplitude. On our next section, my first wave drops back down to not having an amplitude, but my second wave has a +1 amplitude. I add 0 and +1 together. That gives me an amplitude of +1, so my resulting wave needs to drop back down and be even with the +1 from earlier. Now in our middle section, we can see that both waves drop back down to 0. They don't have an amplitude, so that means my resulting wave also will drop back down to 0, and it will not have an amplitude either. So go ahead and pause the video and try this last section and come back and see how you did. I went ahead and labeled each of the amplitudes individually and added them together, and you should have come up with a shape that looks something like this. Now, one of the problems on your test is going to be to add two square waves together, and you will draw the resulting wave like this one. I also wanted to point out that when we superimpose waves together, that is going to be resulting in some sort of interference. So I wanted to see if you could pick out where you have constructive and destructive interference. So let's take a look. For constructive interference, we either want both of our amplitudes to be positive or both of them to be negative. When we look at our wave, that would be this section right here would be constructive interference. The first wave was positive, the second wave was positive, and it resulted in an extra super positive amplitude. Now for destructive interference, remember we want one of each. and that would be in this column. We've got one amplitude that's negative and one that's positive, and those cancel out and result in destructive interference. Our next and last section is on standing waves. This is an additional slide for you. Feel free to pause and write down this definition if you think it'll help. And now we're going to look at the parts of a standing wave. So as you saw in the previous slide, standing waves are the result of identical waves traveling in opposite directions. There are two parts to a standing wave. One part is called a node, and that's the point in the medium that's undisturbed, and it's produced by destructive interference. And then the other part of a standing wave is called an antinode, and that's the point with the maximum displacement, and that's produced by constructive interference. So I have some pictures for you. We're actually going to do a lab in class where you produce a standing wave, and you're going to get a picture that looks something like this. We call these little footballs because they're shaped like a football or a pocket. And when we reach a standing wave that looks like this, the section in the middle is going to be pretty blurry, and it'll look to your eye like there's a solid section, and you cannot actually see the waves moving up and down. They're going to combine with each other such that it looks like this little football. On the end of the wave will be a node, and there's also a node on this end as well. And then the antinode will be in the middle where the displacement is at a maximum. So there are always nodes on the end, and if we have two little footballs, there will be another node in the middle where they meet, and then now we have two antinodes. So however many of these footballs or pockets you have, that's how many antinodes you have, and then the nodes will always have one additional number than antinodes. Again, we're going to do a lab so that you can actually see this in person. I just want you to be able to label the parts of a wave. And lastly, to check for your understanding, I've got a picture here for you of a standing wave. And in this entire picture, I want you to find out how many nodes there are in that section. So take a moment and count and come back and see if you have the right answer. You should have gotten choice C, 9 nodes. And then our last question, of all of these labeled points, where would destructive interference occur out of these choices? So take a moment, look at the picture, and come check your answer. You should have gotten choice A. At points B, C, and D would be when you have destructive interference. Remember, those are where the nodes are produced. So today I know we discussed the different behaviors of waves. Remember to bring your notes with you so that you can use them when we do our labs in class and make those connections between the vocabulary that you learned today with what you're going to see hands-on during our class time.